For our final chapter in the course, we're going to take one final step up to the biggest scale of all, the entire universe. Cosmology is a scientific study of the universe as a whole, from its early history through its current state and on to the long-term future of the universe. The past and future of the universe is something humans have speculated about throughout our history, but only in the last century have we even started to study the universe in a scientific way. In the last few decades, our ability to study the universe has expanded dramatically. In this chapter, we'll take a quick look at some of what we've learned about the past and future of the universe. But we've also got to look at one of the most important constituents of the universe, something we haven't even mentioned yet in the course: dark matter. Dark matter is matter we can only detect because of its gravity, and we're only now starting to understand its properties.
We're going to start by seeing what we know about dark matter. We'll begin with the observational evidence that dark matter exists and its properties. Then we'll discuss what dark matter can and can't be. Then we'll shift the focus to cosmology. There are several possible topics here, but we're going to stick to just two key ones: the expansion of the universe and what it implies for the fate of the universe, and the cosmic microwave background, one of the key observations of the early universe. Cosmology is the study of the universe as a whole. This is the branch of science that tackles the really big questions. Some of these include: how did the universe form, and how has it evolved since its formation? What is the eventual fate of the universe? How did the large-scale structures, such as clusters and superclusters of galaxies and the voids between them, form? What is the overall composition of the universe, and how did this come about? Cosmologists don't have all of the answers to these questions today, but the fact that we can even begin to address questions like this in a scientific way is an indication of just how far our understanding of the universe and the processes that operate in it has developed in the last 2 centuries. It was theoretical developments, like the laws of energy in the 19th century and relativity and quantum mechanics in the early 20th century, along with observations like the expansion of the universe in the early 20th century, the cosmic microwave background in the middle of the 20th century, and the evidence for dark matter in the late 20th century, that have allowed the development of a scientific model of the universe and its evolution. So let's start our look at the universe as a whole by asking a question that should be easy, but isn't. What is the universe made of?
As we've mentioned earlier, we can use orbits to measure masses. We've seen how the orbits of binary stars around each other can be used to find the masses of stars. The same principle can also be applied to stars and gas orbiting around a galaxy. If we measure the speed of a star in a galaxy, we get a good estimate of the mass of the galaxy enclosed by that star's orbit. For example, the yellow curve in the diagram below shows the orbit of the Sun around the Milky Way. The Sun's orbit speed in the galaxy tells us how much mass is within this orbit. By measuring the orbit speeds of stars in different parts of a galaxy, we can make a graph showing the orbit speed at different distances from the center of the galaxy. This is called a rotation curve, and it can be used to see how mass is distributed throughout the galaxy. These 2 exercises should help you see more specifically how this works. The blue circles represent face-on views of the disk of a spiral galaxy, showing 2 possible ways the matter might be distributed. Almost all the matter might be concentrated near the center, or the matter might be spread evenly throughout the disk. The letters represent stars that follow approximately circular orbits within the disk. To start with, put the stars in order of how much mass is enclosed within their orbits from the most to the least amount of mass. There may be 2 or more stars with the same amount of mass enclosed. Now that you know how much mass is enclosed in these orbits, The next step is to rank the stars from fastest to slowest velocity. Remember, only the mass inside the orbit affects the orbit. The stronger the gravitational pull on the star, the faster its velocity must be, or its orbit will be unstable. Distance matters too, because more distant masses exert less gravitational pull. In fact, we see the effective distance in our solar system. The most distant planets orbit more slowly.
Let's take this discussion a step further and see how we measure the mass of a galaxy using the orbits of the stars and gas within it. Back in the chapter on motion and energy, we saw that Isaac Newton took Kepler's third law of planetary motion and updated it so that it could be used to calculate masses in astronomy. The version we saw for planets looked like this, where m is the mass of the star orbited by a planet, g is the universal gravitational constant, and a and p are parameters of the planet's orbit. When we're studying galaxies, we often have different information about the motion of objects inside them, so we rewrite the formula like this. M is rv squared over capital G. The m now is the mass of the entire galaxy, while r is the galaxy's radius, and v is the orbit speed of objects near the outer edges of the galaxy. Once again, capital G is the gravitational constant. In the next few slides, we'll run through an example to see how we use this. Here's a sample problem. Imagine a galaxy that has a diameter of 100 kilolight-years, which is the same thing as 100,000 light-years. The stars in this galaxy are mainly orbiting at a speed of 200,000 meters per second, which we write as 2 times 10 to the 5th meters per second. These numbers are not too far off from the values for our own Milky Way galaxy. As usual, we start by writing down the formula. Just as a reminder, the gravitational constant, G, is given by 6.67 times 10 to the minus 11 meters cubed per kilogram seconds squared. This is a universal constant, so it will always have the same value. The gravitational constant forces us to use specific units for the rest of the problem. In particular, V has to be in meters per second, and R has to be in meters. As you can see from the numbers above, we've got the velocity in the right units. However, we've still got to find the radius of the galaxy and get that into meters. Our next step is to find the radius of the galaxy. We know its diameter, 100 kilolight-years. Remember that radius is 1/2 of diameter, so the radius of the galaxy will be just 1/2 of this value, or 50 kilolight-years. However, we've got to get this radius into meters, since kilolight-years isn't the right unit to cancel the other distance units in G and V. Let's figure out the conversion factors here. First, we know that kilo means 1,000. So 1 kilolight-year is simply 1,000 light-years. Next, back in the very first lecture, we saw that a light-year is 10 trillion kilometers. If you don't remember how many zeros that is, just go through the list. 1,000 is 3 zeros, 1,000,000 is 6 zeros, 1,000,000,000 is 9 zeros, so 1,000,000,000,000 is 12 zeros. That means that 10 trillion kilometers has 13 zeros, and we can write it as 1 times 10 to the 13th kilometers. Since a kilometer has 1,000 meters in it, we can multiply this by 1,000 to find that 1 light year is 1 times 10 to the 16th meters. So to get the conversion from kilolight years to meters, we simply multiply this by 1,000, since there are 1,000 light years in a kilolight year, to get 1 times 10 to the 19th meters. Now we have the conversion factor from kilolight years to meters, so we can use that to find out how many meters are in 50 kilolight years. Simply multiply 50 kilolight years by 1 times 10 to the 19th meters to find that the radius of the galaxy is 5 times 10 to the 20th meters. This sounds like an enormous number, but that's what we should expect here. After all, We're talking about measuring the radius of an entire galaxy using human-scaled units like meters. A galaxy is simply that much larger than we are. Now that we've got everything in the right units, we can go ahead and find the mass of the galaxy. Once again, let's write out the formula. Next, we can put all the values into it: the radius of the galaxy, the orbital speed of stars in that galaxy, and the gravitational constant. Notice that all of the distance units are in meters, all of the time units are in seconds, and there's only one mass unit, kilograms. As we work through this, everything else will cancel out, so that the kilograms is the only unit remaining. As we start multiplying the values out, the numerator becomes 2 times 10 to the 31 meters cubed per second squared. Then we divide that by the gravitational constant, and that gives us 3 times 10 to the 41 kilograms. Of course, 10 to the 41 kilograms is once again an enormous number, so we need to convert this into a more meaningful set of units. Remember that one solar mass is 2 times 10 to the 30th kilograms. So when we divide the galaxy mass by this, we find that the galaxy is 1.5 times 10 to the 11th solar masses, or 150 billion solar masses. This is a fairly typical large galaxy mass, so it looks reasonable here. In general, we find that galaxies range from a billion up to several trillion solar masses. If you get an answer that is well outside of this range, you should probably check your calculations, especially the unit conversions. Now go ahead and try calculating the mass of this galaxy. First, see if you can predict whether it will have a larger or smaller mass than the galaxy in our example. Compare the numbers and think about how the mass needs to change to get this size and speed. Then go ahead and calculate the actual mass. To understand what a rotation curve can tell us about a galaxy, let's look at 3 different types of rotation curves. One is a solid body rotation curve. If the galaxy behaved like a single solid object, it would have a rotation curve like this one, with the slowest speeds in the center and faster speeds closer to the edges. A spinning ball, or a spinning planet, has a rotation curve like this. Another rotation curve is the solar system curve. When virtually all of the mass is in the center of the system, then the orbit speeds get slower as you get farther from the center. Remember that gravity gets weaker as you get farther away from a massive object. As the name suggests, this is the pattern we see in our own solar system. A third option is the constant speed rotation curve. Instead of all of the mass at the center, there's only a small amount in the middle, with more spread out farther away. A star in a more distant orbit is pulled by more mass than one in close to the center, so the speed doesn't drop off the way it does in the solar system curve.
When we look at our galaxy, or most other galaxies like it, we see that the vast majority of the stars are in the bulge. That's why the bulge is so bright in this infrared image of our galaxy. So what we would expect is that the Milky Way's rotation curve should be fastest in the bulge and then drop off as we move out through the disk. This would make it look a lot like the solar system model we saw a couple of slides ago. However, as we just saw, the actual rotation curve is fairly flat, not just in the bulge, but all of the way out to the outer edge of the disk and beyond. This tells us that there is a lot of mass in the galaxy that is not in the form of stars, and this mass is not concentrated in the bulge of the galaxy. Instead, it's spread out throughout the Milky Way. When we look at other galaxies, we see the same pattern. The rotation curve is flat out to the edge of the visible disk, suggesting that mass is spread out throughout that galaxy rather than concentrated in the center like the stars. The name we give to this unseen mass is dark matter.